Okay, so there are two ways to do D. First one is just like this. Okay, just use 98 divided by 2. Okay, from the formula. Okay, GFW over Z. Another way is like this, showing in the PowerPoint slides. If I have the GFW of sulfate, so this is SO4, 2 minus, without hydrogen. Okay, the sulfate, so this is 98 is the GFW of sulfuric acid. Okay, but in this case, we just want to know the GFW of sulfate. Okay, so it's 96. Okay, and the moralities of ammonia sulfate is 0.5. Okay, and based on the formula here, you can see that. So it just got one sulfate, right? So it's also equals 0.5 moles sulfates per liters. So mass over liters equals morality times GFW. So that's 0.5 times 96. So we got 48 here. Okay, I can show you another solution for calculate this. So other solutions. So NH4 to SO4, ammonium sulfates. The molecular mass is 132, right? And SO4 2 minus is 96, as we just calculated. So the ratio of sulfate in these compounds is 96 over 132. Okay? And let me go back to the question, okay? In this question, we have 66 grams, right? So, times 66. Then we got 48 grams per liter. This is another way to calculate. Okay. If you think this is easier. But actually they are the same. Okay, they are the same. Alright? So this is another way to find the answer. Finished? Okay. Question E. Let's see. Question E asks us to find out the gram per liter. Gram per liter as N. The N here is not normative. The N here is nitrogen. Note that. The N here stands for nitrogen, not normative. So let's see. Let's see these questions. So based on the formula, how many n we have in this formula? 2, right? So we have 2n. Question E. So first off, let's find out the nitrogen mass. So it's 2 times 14. So we got 28 here. So the ratios of nitrogen equals 28 over 132. It's similar like this one. So 66 times 28 over 132. We got 14 grams per liter. Okay? The mass of nitrogens. Okay, the reason we have 2, can you see here? Okay, we have 2 nitrogen in this chemical formula, right? The atomic mass of nitrogen is 14, right? So 2 times 14, we got 28. The ratio of nitrogen in these compounds is going to be 28 over 132. And we got 66 grams of this sample. So we got 14 grams per liter. Everyone okay? Okay, this is another way. Okay, you can choose either one. Okay, I think this one is easy to understand. Okay, so we have 0.5 more, right? And we have 2 nitrogens. So nitrogen actually occupy 1 mole. Okay, then 1 times 14. The atomic mass of nitrogen, or the so-called GFW. So the answer will be 14. Okay, either way is fine. You can choose this one or this one. Either way is fine. Understand? You okay? Okay, let's move on to this the gas sample. Okay, gas. Student, when gas come to your minds, it got very important characteristics. The gas is compressible. Right? The gas is compressible. Okay? So for example, like we have 0.056 milligram ozone per 1 meter cubic air. So there are 2 kinds of ppm that we can express in these questions. Okay? So first of all is mass basis. So we have a subscript. What is subscript M here? The subscript M here means the mass basis. Okay. So for the mass basis, the ppm M equals the mass of pollutant over mass of air sample. Because gas is compressible, so two important key points that you need to notice. This first one, the volume is not constant. The volume can be changed. Okay, volume changes. And the second one, the density is not constant as well. Because your volume changes, so your density is impossible to be constant. So in this case, the ppm is not constant. So it doesn't seem suitable, okay, for an air sample like this. You use mass basis, right? So this is no good. For the air sample. Okay, but good for solid sample, right? Because solid is incompressible. So for the gas samples, we like to use the volume X. So we have a subscript B here. So everyone okay with that? Everyone okay? May I remove this? So for the volume basis, the ppm V equal the volume pollutant over volume air sample. Okay. And the good thing for using the volume best, because this formula is going to be independent of pressures and contractions. Why? Because as the volume shrink, the mass reduce. Understand? Understand? Based on the ideal gas law, right? Volume is proportional to mole, which means the volume is proportional to the mass. So if we use the volume basis, both gas volume shrink proportionally with mass. So this is going to be constant. Okay? So this is good for the gas sample. Okay? Keep this one in mind. If you are dealing with the solid sample, okay? If you're, maybe I just write down here. Usually, okay. Good for solid and liquid. And volume mass good for gas. Okay? You understand? Everyone understand? Yeah, may I move on? Okay, based on the ideal gas law, okay, PV equal nRT, right? So just rearrange V equals N times RT over P. So at 1 atm, okay, at 0 degrees Celsius. 0 degrees Celsius equals 273 Kelvin. Okay, in this case, 1 mole of gas sample. 1 mole of gas sample equal 22.4 liter. Understand? How to calculate this? This is super easy, okay? PV equals nRT, right? So P supposed to be, we assume 1, right? The volume is what we want to find out, right? So assume 1 more as well, times 0.082 times 273. So the V will be 22.4 liter. Okay? Okay, right? So let's do this convergence. So let's do convergence. Let's convert the mass to mole. Okay. So this problem states that we have 0.056 milligram ozone over 1 meter cubic air. Okay, and we want to convert the milligram of ozone into mole. Okay, we want to convert milligram of ozone into mole. So everyone might know this, right? The mole equals mass over molecular weight, but over molecular weight. Okay, and the mass should be in grams. The mass should be in the unit of gram. So we got 0.056 times 2 minus 3. Okay, times 2 to the power minus 3. Divided by 48. Okay, divided by 48. Then we got 1.17 times 2, 10 to the power minus 6. Okay. So this fits the scientific notations. Okay. The value here should be larger or equal to 1, smaller than 10. So if you show this, if I ask this question, you show this in your answer, I might take off 1 point, okay? Because this doesn't fit the rules, the format of scientific notation. Okay, next questions. If we want to convert it into the volume mass ppm, okay, into volume mass ppm, as soon as we need to assume this. As soon as 1 atm, 0 degrees Celsius. In these conditions, we call it STP. STP stands for standard temperature and pressure. So STP stands for standard temperature and pressure. Okay? So we have this amount more, right? And times by the numbers, the conversion factors that I just told you, right? At 1 atm, 0 degrees Celsius, 273 K. So one more equals 22.4, right? And we have this amount more. Okay? So this equals 0.026 times 10 to the minus 3. Not finished yet. We also need to convert this into liters, right? So we have, one meters student, 1 liters equals 1,000 milliliters. Okay, 1 liter equals 1,000 milliliters, right? So equals 1,000 centimeter cubic. So 1 liters also equal 1,000 centimeter cubic. So in this case, 1 meter cubic equals 1,000 liter. 1 liter equals 1,000 milliliter. And 1 milliliter equals 1 centimeter cubic. So 1 liter equals 1,000 centimeter cubic. So 1 meter cubic equals 1,000 liters. Okay, after that we can get 0.026 ppm. Don't forget about the subscript B here. And if you want to convert into ppb, the value is gonna be 26. Okay. So let me conclude here. Why ppm V is good for gas? If I ask a quick response question like this, okay, then you just give me very short answer. Okay. Number one, because gas compress. Gas compress. Gases compress and expand. Number two, if we use volume mass, the volume ratio stay constant under pressure change. So the pressure change doesn't mean anything. Understand? So if we use mass basis, the pressure changes will affect the mass. So the ppm m, the ppm, the subscript m, will be changed all the times. Is that constant? Okay. Okay, and everyone okay? And beside this number, let me give you another one. At still 1 atm. However, 25 degrees Celsius. 25 degrees Celsius. Then one more of gas sample equals 24.5 liters, right? 24.5, right? Yes, 24.4 something, 24.5. Okay, everyone okay with that? May I move on? Okay, I would like to move on, okay? So in this, the reason I want to review these calculations, okay? Because we will be dealing with the greenhouse gases, okay? Including like carbon dioxide, methane, nitrous oxides, okay? And the CO2e, the E here stands for equivalence. The E here stands for equivalence. Okay, this means the E here stands for equivalence. This means the different greenhouse gases trap the different amount of heat. So to compare them, scientists convert everything. Okay, scientists convert into everything in equivalence, carbon dioxide warming effects. Okay, so the E means to compare those things. Okay, so convert everything. Convert everything into equivalent carbon dioxide warming effect. So this is CO2e. Okay, the next slides show you a terminologies called global warming potential. So GWP. Global warming potential is used to measure how much heat a gas traps compares to carbon dioxide, okay, over the time. Typically, for example, like 100 years. Typically 100 years. So in these slides, we learn terminologies. This is also in the textbook. I hope everyone, if you want to if you don't want to purchase the hard copies, at least you need to find electronic versions on internet. I think you can find all versions on internet. Okay, you need to read. Okay, so we have a terminology shown in this PowerPoint slides. It's called global warming. So how many Taiwanese students still here? There are lots of Taiwanese students. Taiwanese students 不是热手吗？还是有一些啊。哎，你们听得懂吗？可以吧？我有故意讲慢一点，可以啊。好，听不懂再问我。你们要看书啊，好不好？你们要看书，都从书出来。Okay, so we have terminologies. It's called global warming potential, GWP. So the GWP means the measures of how much heat gets trapped compared to carbon dioxide over a specific time period, and typically 100 years. Okay? So for example, like, so you finish this, everyone? So for example, like, the gas and the GWP modifier, and because we use carbon dioxide as a standard, right? As a gold standard, we compare to this. So the GWP modifier it should be 1. Okay? And max sense will be 25. And nitrous oxides will be 298. Okay? And the rest of this three will be very terrible, like hydrofluorocarbons. You're gonna have 124 to 148 sour. 124 sour, okay. Okay, let me just put a maximum value. Okay. You don't need to memorize this. You just need to have ideas like this. Okay, and PFCS is 122, 12, 200. Sorry. And SF6 is going to be 22, 800. Okay, you don't need to memorize those numbers, you just need to have a rough idea. So compared to carbon dioxide. So what does this mean? This means one molecule of SF6 will trap 22,800 times more heat compared to carbon dioxide. Okay, so it's very severe greenhouse gases. Okay? Okay. So how about our Earth's atmospheres? Okay. So our Earth's atmosphere, we have like 78% of nitrogen, and around 21% of oxygen. So the rest of them occupy around 1%. Okay? And among this, 3 of them, this one, carbon dioxide, this guy, and this guy. Okay, these 3 guys are greenhouse gases. Okay? So as I told you, greenhouse gases exist. Greenhouse gases actually is a good guy. Without greenhouses effect, the temperature on the surface of Earth is going to be super cold. But the problem is, we human beings make greenhouse gases severe, and it becomes a bad guy, and it causes something called global warming. Okay? Okay, next, I'm going to introduce this. Is the so-called oxygen demand. The oxygen demand. And the first one is called theoretical oxygen demand, THOD. Okay, the THOD is the amount of oxygen. The amount of oxygen required to completely oxidize organic matters. Okay, organic matters, the materials. Normally, organic matters. Okay, required to convert. How to convert? Oxidize. Oxidize to carbon dioxide and water. To carbon dioxide and water. Okay, for example, glucose oxidize into carbon dioxide and water. 6, 6, 6. Okay, so this is so-called theoretical oxygen demand. Calculate theoretically from the chemical formula. Okay, and we will assume complete oxidations. We will assume, can you see the writing here? The student in the back, can you see the writing here? So we assume the complete oxidation. In this case, normally the value of THOD will larger than what we are going to introduce DOD. Okay? So the THOD is normally larger than BOD. Okay? The THOD, you know TH stands for theoretically, right? 理论值啊，理论的。So we calculate from the formula, and we also have some assumption, for example, like this is complete oxidation. So the value of THOD will be larger than BOD. So the second one is called, everyone okay? May I move on? The second one is called biochemical oxygen demand, BOD. So BOD is the amount of oxygen, the amount that's consumed by, this is very important, microorganism. Microorganism. Okay? So we, I don't know if we can do this week. Probably next week, I'm going to, I don't know if you have some biology background. Okay, if not, it's fine. I'm going to have a very quick reviews, okay, to give you some biological backgrounds, biology backgrounds, okay, we are going to use in my methodology. So consumed by microorganisms, while decomposing those biodegradable organic matters. Okay? And BOD is very important. Okay? Because BOD indicates BOD equals biodegradable pollution strengths. So you can regard BOD as biodegradable strengths. For example, like I don't want the BOD value. So the drinking waters, let's compare drinking water and river water. The BOD of drinking water must be smaller than 1. Otherwise, many people will get diarrhea. Okay? And for the river water, it's probably around 2 to 8. And west waters, the BOD will be huge, like 200 to 400. Okay? So the smaller the BOD, the more suitable for human being to drink. Okay? That's the reason I say you can regard BOD equals biodegradable pollution strengths. Student finish? May I move on? Okay, next slide. Next terminology is called COD. C stands for chemical. Okay? So COD oxidize. Okay. Let me try to explain this. COD equals oxidations of almost organic. Organic compound. Okay, I think this is easy to understand in this one, right? In this description in the textbook. Okay. So this is gonna including let me finish this. Including once microorganism cannot degrade. Because the one microorganism degrade, we call it BOD, right? The ones microorganism cannot degrade, we're gonna call it COD. Okay? Okay, let's take a short break. Now it's 3:10. Okay, now it's 3:10. Let's have a short break until 3:20, okay? So I can dismiss class at 4. Okay? At 4:10. Okay, so let's have a break. Let's have a break from 3:10.